So today we are going to discuss one of the interesting welding processes, that is the explosive welding. So the name indicates the explosive welding. Here the joint is actually achieved by the explosion of heavy energy explosives like RDX, TNT, etc. are used for this purpose. Because of this, it makes interesting this process. So now let us see the details of explosive welding. And first of all, if you are asking what is explosive welding, basically this is a solid state welding process. That means the metals are not melting together, but the joint is formed by this plastic deformation of the materials. Now in explosive welding, actually one plate will be kept stationary and another metal will be thrusting with very high velocity achieved by the detonation of the explosive. When one metal strikes over the another, the deformation happens and a metallurgical bond is created uh, at the interface of the material. So in short, you can say explosive welding is a solid state welding process where the joint is made by striking one metal on another material with very high impact, and this is achieved by the detonation of suitable explosive. So now this figure shows the basic things regarding the explosive welding setup. You can see here there are two plates, flyer plates and parent plates. One is in blue and another one is in gray. Basically that are the two plates which are going to be joined. Now explosive will be distributed over the flyer plate, over the blue plate, and when the detonation happens, that portion will be coming and striking the stationary plate, that is a parent plate. Then the joint is happening at the interface. This we will discuss detailedly later. Now where it is used, basically explosive weld is not commonly used for all the purposes, but this is very exclusively used in some areas like very large and difficult to weld components, very large surface area components. If you want to joint, you can use this process. Then another area is dissimilar materials. Always dissimilar material welding is very difficult. For example, if you want to join tantalum to steel, there is a variation in the melting point, because by the time tantalum melts, the steel will vaporize. So this process can be used there in dissimilar material joints, and in some nuclear and space application also you can use this. Now how this is done, this figure shows the basic setup for a explosive welding process. So basically you can see two plates, target plate and a flyer plate. Basically, and these two plates are actually the plates which are to be joined using this welding process. And why this is known as flyer plate and target plate? Because flyer plate is the metal plate which is coming with very high velocity and hitting the stationary plate. So in fact, the explosive is uniformly spread over the flyer plate, and when it detonates, it attains very high velocity and it will come and hit the stationary plate. So that is why the flyer plate, name flyer plate. And target plate means the flyer plate will always thrust towards the stationary plate, and that is a target. That is why the target plate. So basically a flyer plate when comes and hit the target plate, the joint. Okay, so never forget the name, target plate and a flyer plate. So now anvil, you can see the function of the anvil is to support the target plate. Then you can see here buffer plate. So basically when an explosion happens over the metal surface, there can be some damages due to the explosion, and after the joint formation this component has to be used somewhere. Therefore we have to protect the surface of the flyer plate from the explosion. So buffer plate, the function of buffer plate is to protect the surface of flyer plate from the damages caused by the explosion. And one of the important things regarding the explosive welding setup, you can see the standoff. So standoff is the distance kept apart between the flyer plate and the target plate before the welding. So As far as the explosive welding is concerned, the standoff is a very important thing that we will discuss, because this is a very important process parameter. You have to keep the standoff accurately and correctly for getting the proper joint. So these are all the things we have discussed: flyer plate, target plate, buffer plate, and standoff distance. Now basically in this process you can keep two types of standoff, that is parallel standoff and angular standoff. As you can see in the figure, the parallel standoff, both the flyer plate and target plate will be kept parallelly. But in angular standoff you can see the flyer plate is kept at an angle compared to the target plate, so that there will be an angle of approach for the flyer plate to the target plate. And why these two types of standoff means, there are situations where slight changes in the explosives type of materials, the joint strength required. Based on this we will select any of these two type of standoffs. Now these are some YouTube links. You can check this, where some animations and videos, and you will be more clear about the physical processes carrying out in the explosive welding process. Now if we are going into the details of the theory behind the joint formation, you can see these are the two important things with the weld interface and surface jetting. These are the two things happening in the joint formation. So there can be basically two types of interface can be formed in the joint, that is flat interface and wavy interface. Now why these two types of interface are forming? Basically the important thing we want to form the joint using explosive welding is the velocity with which the flyer plate is traveling. So based on that velocity, the joint formation also will be different. So now you can say the entire surface of the flyer plate will not come and collide with the target plate. At a time, one point will be in contact with the target plate, then the next instant next point will be in contact with the target plate. That means there is a point known as collision point throughout the welding process, because this collision point also traveling according to the detonation of the explosives. That means the entire explosive is not exploding at a time. From one end we are detonating and the explosion proceeds. Same way the collision point also moves along with the detonation velocity. That means these two interfaces, flat interface and wavy interface, depends upon the collision point velocity. That means the velocity at which the collision point moves in the joint. So there will be a critical value for the collision point velocity, and a flat interface is produced if the collision velocity is below the critical velocity. On the other hand, if the collision velocity is above the critical value, then you can say a wavy interface is produced. So comparing wavy and flat interface, the wavy interface often gives much better weld joint and properties for the weld. Now the other thing associated with explosive welding is the phenomenon known as surface jetting. So that means whenever two metal plates comes and hits together, then in front of the collision point where the two plates meets, that is a collision point. In front of the collision point you can see a metal jet is forming. That means along with metal, and if any oxides or contamination is there, that will be combined, and inside the small gap between the plate there will be a jet formation. And as the detonation proceeds and collision point proceeds, this jet also will be traveling, and finally when the welding is completed, the jet will be expelled from the material. And the thing you have to note down is, as far as the explosion welding is concerned, this jet formation is very much important, because for the proper joint has to be produced, the jet should be formed. So in this figure you can see the jet formed in between the two plates, and this figure shows some explanations on the basis of velocities achieved by the different plates, because here lot of velocity components are acting. Now let us say the plate 1, plate 2 are the flyer plate and target plate respectively, and point C you can see the collision point, so where the two plates are actually meeting at the instant. So now you can see the Vp is the plate velocity, flyer plate velocity. So the flyer plate will be coming with the velocity Vp and it collides at the point C. Then you can say the target plate velocity will be Vb. So depending upon these velocities, a jet will be formed and the velocity of jet will be Vj, and we can see the direction of jet also. So that is regarding the jet formation, and the lower figure shows the velocity diagram for the jet formation. So the slide explains some condition for the jet formation. It says the impact velocity becomes the plate velocity. That means when the impact occurs, that velocity should be become the plate velocity. Also, that velocity should be high enough to exceed the yield stress of the material. Simply says, whenever the flyer plate with a velocity Vp comes and hits the target plate, then the impact velocity and Vp should be same. Also, it should deform the material. That is why it is said that it should be above the yield point. Then only the deformation of material happens and the joint occurs. Okay. Now next is the collision point velocity should be less than the velocity of sound in both the materials. If these two conditions satisfies, then the metal jet and a wavy contour is occurs and you will get a good joint. Again, this figure is used to explain the jet formation and how the joint occurs. Again, I am telling you the entire surface is not joined at the same time, because the explosive is detonated from one end and it progresses to the other end with the detonation velocity. In the same way, as the detonation progresses, the metal plate also hits the surfaces at collision point. So this is a progressive process. Now these are the different stages in the explosive welding. You can clearly distinguish into three stages: stage 1, stage 2 and stage 3. Stage 1 is the basic setup for the explosive welding process. The target plate is kept on the anvil, then the standoff is maintained, and here it is, you can see angular standoff is maintained. Then in the stage 2 you can see the detonation happens. From one end the detonation happens, that means the explosive is getting detonated. In very basic terms, explosive is getting ignited. That is with the velocity Vd. That means the detonation velocity. Now as the detonation happens, you can see now the flyer plate is getting some amount of velocity, that is Vp. Then you have to note down is the velocity is achieved only at the portions where the detonation happens. Okay. So now whenever the Vd is formed, that is the detonation velocity is formed, Vp also formed, and Vp is in the direction towards the target plate. Now the flyer plate having a velocity Vp will come and hit the target plate with enough velocity. You can see here the values of collision point velocity Vcp is equal to Vp by sine gamma, that is gamma is the angle of approach. So then you can see wherever the detonation happens, that much area is now joined to the target plate. That means joint is formed on that much area. Progressively as the explosion progresses, the remaining portion of metal also will be hit the target plate and the joint will be completed. So this will be more clear when you are watching the video I have given in the previous slides. So now we have discussed the detonation velocity. There is a velocity with which the detonation proceeds. What is the importance of detonation velocity? So as a basic rule, it says the detonation velocity of the explosive must be less than 120 percentage of the sonic velocity of the material. That is, every material will have a sonic velocity. That means the velocity at which the sound waves travels. The detonation velocity should be 120 percentage less than of that. If not, there are two conditions. If the detonation velocity is greater than 120 percentage of the sonic velocity, a shock wave will be developed, and this will affect the welding because shock wave will create uneven pressure distribution, and this will lead to the shock hardening. So once the shock hardening occurs, deformation will be very less and the joint will not be formed. That is one condition. Then the next condition is the detonation velocity is 100 to 120 percentage of the sonic velocity. So first condition was above 120, now it is between 100 to 120. In that case, a detached shock wave occurs. A detached shock wave is occurred and which travels ahead of the detonation. So as it is traveling ahead of the detonation, it won't create that much problem as the shock wave, attached shock wave. And then the next condition is when the detonation velocity is less than sonic velocity of the material, then no shock wave is produced. Okay, so this is the importance of detonation velocity. Three conditions are there. In the last two conditions, we don't have much problems with the detonation velocity, but the first condition should be avoided as far as possible. Now coming to the process variables, important parameters that affects the process is the impact velocity, standoff distance, and the angle of approach. So impact velocity, already we know what is impact velocity, the velocity with which the impact happens. Always there is a minimum velocity for each material below which the welding does not take place. So always our impact velocity should be above the minimum value, and this velocity you can see depends upon the ratio of weight of explosive to weight of flyer plate. That is obvious. And the maximum velocity that can be employed will be depends on the velocity of sound in the material, and the minimum velocity is depending upon the magnitude at which material becomes sufficiently plastic. So here again I am stressing that basically this joint is formed by the deformation of the materials. So this minimum velocity should be like that, it should create enough amount of deformation. So that is why the minimum velocity is decided by the amount of plastic deformation and on impact and to form the material jet. Now standoff distance, in the earlier slides we have discussed the standoff distance is an important parameter. Now if we are increasing the standoff distance to above certain level, what happens is it results in the increased size of the wave. That means wavy interface, the waves will be increased size, then that affects the joint. So standoff distance you have to keep it correctly, but you can use a less standoff distance if the explosive is having a very high detonation velocity. Now angle of approach, in angle standoff, the angle of approach, in the previous slide that gamma was the angle of approach. Definitely as it varies, the joint formation also will vary. So basically for successful welding the angle is kept between 5 to 25 degrees. Now these are the applications, it is used for cladding, etc. Then the advantages of explosion welding is very large workpieces can be welded, dissimilar metals. Then the melting temperature, coefficient of thermal expansion differences do not affect the final products because not much affected with the heat, therefore these are not all a problem. Then it is compact, easy to maintain, and these are the disadvantages. Ductility should have, the material should have ductility. The geometries are constrained because usually we prefer flat surfaces, then cylindrical and conical. Other complex geometries are very difficult to weld. Usually we prefer only flat surfaces. At sometimes you can go for cylindrical and conical. Then the cladding plate cannot be too large. Then the noise and blast. This is actually using heavy energy explosives. Then the blast will be very critical, so that the protection of workers and all the things will be a problem. So that is regarding the explosion welding process. Thank you.